I wrote it before.
Okay. Am I on?
You are on.
Okay. All right. Hello, everybody. Okay. I think we have a great request that asked me to do the 8080 project from the very beginning. Okay. And I think that's a good thing to do. And I think if we have enough time, I'll show you the PDP-1 project. But let's first run 8080 from the very beginning. Okay, from this screen. Okay, do I have to reboot my computer? Okay, don't have to do. All right. So here. Oh, okay. Yeah, the to get IDE, the Diamond IDE to run, you have to first get to Lattice Semiconductor website. It's www.lattice.semi, and then go to the tools, I think, and get the Diamond IDE downloaded. But when you want the Diamond IDE to run, you have to have a license, and the license is free. And probably you can give us exactly procedure of getting the license.
From the newbie perspective.
Yeah. You just said yeah.
I'm looking, but essentially when Lattice, it asks you to choose a license. I found that I didn't want the floating license. I needed a node locked option. And then when I went to Lattice, it asked for your MAC address. So I had to go and find the MAC. And then check long enough to enter it. And then it will give you a license.dat file, which you download, and you then go to run the Brevia software, Lattice Brevia software, and when it loads up, the Diamond software will ask you where that folder is, where you've put the license.dat file, and then it'll come up and run.
Okay, thank you.
Because of something I had read, it said it, but I don't know that. That's why I'm saying maybe it didn't seem to work when I tried it, but it did work for you. Okay,
it worked for me.
Okay.
The node lock. That's the only one I know works.
Right. That's because that's a good reason.
Yeah. I think they specified it because there was some other wording on the last site that said if you have a floating blah 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 blah. When I got to the blah blah blah, I went
Yeah, I think the floating license is generally for a company.
Yes.
Okay, if you are a company, lots of people are using the IDE, then you can get one floating license, and everybody can share it. Okay.
Right. If you're buying a license.
Okay. Yeah.
Then you can buy so many seats.
Okay.
And there you want floating license.
Yeah. Okay.
If you want it, but for this free one, I believe it is you have to do the node lock.
Okay. Okay. Yeah. All right. Okay. So what I'm trying to do is from this Windows screen, try to bring up a fresh project and try to get it run. All right. It's kind of a challenge, but I think it is probably a very helpful thing for people who just started. So here I'm loading the Diamond. Takes a couple minutes. Oh, well, yeah, because I have already loaded before. So you get this start page, the start page, and you have I'm having lots of projects there. I got 2 PDP-1 projects and one 8080, but these are not the ones that I'm going to open up a new project, okay, and imported all the files, and then try to do the synthesis. Okay, so there I want a new project. Okay, open a new project. It will ask me, okay, here is I wanted to do let me see. I want to do a EP8080 Y project because I have an X project there. I hope it will open up. Okay, I better EP8080 Y. It's going to be a new project, I think. Source file. So it's asking for source files. Okay. I think add source file. And I'm going to copy all the source file from the EP8080X project. These are pretty much all the files that I distributed. Okay, so I will have 5, the EP80 chip. This is the top level, and the EPGIO and the UART. So these and chip and memory, RAM memory. Okay, so these are the files I need to open. Yes, these are the minimum files. Yes, yes.
Can I download these?
Download these, I think, yeah. In here, there is a workshop folder. Just download everything, workshop folder.
Okay.
All right. I think there is another file, which is let's first loading these files. And then I make sure that the copy source to implementation directory. Okay, so these are the files from another project, and I just want to import them in, but I want to make a copy of it in the current project. Okay, then it asks for the chip. This is Lattice XP2. And I think it's Lattice XP2. And it's LFX. Okay, it's LFXP2. So that's the chip used on the Bravia board. All right, so this, see next. Okay, so it asks you to see the synthesis tools, and we use the Lattice synthesis tool. And it gives you options to select other tools, but okay. So we have loaded the project. And once all the files are loaded, it actually does the synthesis automatically. Okay, it looks at these 5 files and it finds that the top level is the EP8080 underscore chip. So that's a top level design. And the other 4 files are components, the CPU module, memory module, UART module, and the GPIO module. So these are all loaded up, and you can see it in the hierarchy window. Okay, let me open up this a little bit. And so here are all the input files. Okay, and these input files are, yes.
I was with you up to that point, but I only see the hierarchy window. I don't see how did you get the other 2 windows?
Okay. If you don't see this, go to the view. Okay, and open the process window and also the file list. I think you want what I'm going to. You have to have these 2 windows because they are important in selecting different synthesis options. Okay. So here the file list shows you all the 5 files, and the highlighted file is the top level module. Okay, so you have to have this one highlighted in both phases. Okay, let me just show you a little bit here. If you double click on any of the files, I think it would open. Okay, now it opened up the top level. Okay, so it declares an entity, the EP8080 underscore chip. This is the top level design, top level module. And it has all the I/O signals that this chip have to communicate with the rest of the components on the Bravia board. So we have the clock, a reset, UART input, UART output, and I/O pins. Because the memory module is inside, it's a sub-module here. So the memory signal does not go out. Okay, and we implement all the memory inside the chip. So we don't need external memory. And so memory bus and data bus are not brought out. So this is the top module. And the next one is the CPU module, EP8080. And then this is the memory module. And then the UART module and the GPIO module. Okay. And then here it shows you instantiate all this module in your design. And then you assign the signals into the module and out of the module. Okay, so you have to interconnect all the modules together. For example, this is the CPU module. The CPU module takes the clock and reset signal, and then produces CPU data. It produces address and the data out, and it is expecting data from the input port data I, and it also produces a read signal and write signal to read and write the memory. So these signals has to be routed into the memory chip. And so here is the memory module. Okay, it shows that its input is taking, it has the address. Where does the address come from? it is generated by the CPU on the bus CPU_add DDR_O, and that's a 13-bit bus. So I'm using 8 kilobytes of memory, and the data, that's the data input. That's from the CPU data out, and the memory data output is produced from the Q port in the memory module. Okay, so this connects the CPU to the memory, and then the UART and GPIO very similarly. Okay, let me show you the EP80. This design is the so the entity declaration, you specify all the input and output signals from this module, and then the followed by implementation. You have to declare all the signals that you used inside the design, specify them if they are single bit logic or multiple bit logic, what they call STD logic vectors. And here are constants. These are constants are used to select the functions in the multiplexers. Okay, you know the design is that we have a set of registers, and in front of each register there is a multiplexer, and the multiplexer takes signals from all over the chip, and then you have a select signal for that multiplexer. So you select the proper signal to this register, and on the rising edge of the next clock, the data that you selected will be latched into this register. Yes.
Is it at this point that you could edit, for instance, the error that Mr. Collins found could you edit this file then at this
yes.
point to correct that?
Let's don't do that.
Okay.
Okay, because I'm afraid I'll get the wrong place and get the wrong number. Okay, let's don't be that brave. Okay, so here are all the select signals defined as constants, and then here are all the multiplexers. That's for example here, it's a source select. This source, I think it goes into one of the ALU. That's one of the ALU input, and this source select one of the 8 registers A, B, C, D, and H, L, and P as input. Okay, and so this one goes into the ALU as part of the ALU select. Okay, so these are all the multiplexers. So the multiplexers select proper signals to be latched into each and every data registers. And if you just go out to the memory, if you are writing to the memory, you have to set the write signal to 1. Okay. Otherwise, most of the time, if write is at 0, the CPU is just reading data from the from memory or I/O. Okay, here is where the instructions are defined. It is a process, a decode process, and the decode process basically to execute one instruction. What do you mean by one instruction? This particular instruction will select the signals for all the registers that need to be changed. Okay, so here these are all the select signals, and all the select signal defaults to 0. We set it to 0. 0 is generally the most prevalent activities that has to go on in this multiplexers. And this load signal, every register has a load signal. If the load signal is at 0, the register doesn't get changed. If you need to change any register, that load signal has to be set 1. So this is what an instruction does. Instruction does is set the proper load signal to indicate which register it needs to be updated, and then set the select signal to route the proper signal into the proper register. Okay, now here are all the instructions. So here the instruction I have the case. Okay, code is 0 to 6. The top 2 bits of the instruction signify the type of instruction it is going to execute. So here, no op or 0, that's a no op. If the first 2 bits are 0 and the next bits are 110, 111, then it's a store. It's a store command. Then the next one is a CRC and so forth. So I think the problem was in the increment and decrement. Probably in this area that I specified the source P incorrectly, but I'm not sure. Okay. So this instruction is to select the proper multiplexer in front of the proper register, and then give the proper load signal, so that on the rising edge of the next clock, the data selected by multiplexer gets loaded into the proper register, and that's all instructions are doing. Okay, so specify the multiplexer select signal and the register load signal. So that's all they're doing, and this go through all the instructions. Okay, then here, the last but not the least is the finite state machine. This thing controls the clock, not the clock signal. This controls how the instructions are sequenced through. Okay, so here is the unclear is a 1. That's a reset. It clears all the registers into the reset state, and then you can specify what goes into the registers. Okay, so the most important is P register got a 0, so it starts from memory 0. Okay, and all the other registers, you can initialize them any way you want. Okay, you can put in any pattern in the registers, because most of these registers get changed when the program is running. but it's nice to have some initial data there to help debugging. So you know that I have this register on the reset, and if it got changed, it has to be changed the right way. And I think you have a question is that you have 64 words of memory, or 64 registers if you implement it that not as memory but as registers, and you can initialize them here. Okay. And now this is the initialization, and after the clear signal is released, you start to execute instructions. How do you execute the instructions? You control the signal, the clock signal comes in. So clock tick event, and the clock equals to single quote 1, single quote. And this specifies the rising edge of the clock. So on the rising edge of the clock, what do? You take the next phase and put into phase. So in each instruction, if it is a multiple cycle instruction, it will set the next phase, a variable next phase. And this next phase will be put into phase. And this phase will be used by the decoder to decide, you know, if in the phase 0, what should be do, what the CPU have to do. If in the phase 1, what the CPU has to do. If it in the phase 2, 3, 4, depending how many phases. But each instruction, if you don't mention next phase will be 0. It automatically set to 0. So these are automatically executing the one cycle instructions, unless this instruction changes the variable next phase. Okay. Okay, when that's taken care of, then it's just looking at the load signals. Any of the signal is a 1, then we write the input to the register. Where does the input come from? The input comes from a multiplexer, and the source from the proper signal out of the multiplexer is selected register select signal. The CPU gets the specification gets very simple. You just see which load signal is a 1 and write the signal into the proper register. And that's all of the CPU. Okay. You have the input output specified in the entity, and you have concurrent logic which runs all the multiplexers. Okay, that's a concurrent part, and you have the sequential part which specifies the instruction. When each instruction, which select signal it needs to specify, and which load signal it has specified. Okay, and then you get to the finite state machine part. That means on the rising edge of each clock, what happened? Okay, and what happened is that if any of the register has a load signal set to 1, you copy the input to the register, and that's what a CPU is doing. Any question, comments? Okay, now this has already been synthesized, and it says 0 errors and 0 warnings. Okay, So that's everything's okay. If there's anything, if there's any error, it will not go to the next step. If there's some warning, it will allow you to do the further experiments. To watch out, because the warnings sometimes are quite important. So try to eliminate all the errors and try to eliminate all the warnings, and make sure that at least the synthesizer agrees with your logic design. Okay, so the next thing you want to do is to do the simulation. Okay, to do the simulation, it is this process part. Okay, there's lots of processes you can select. Okay, and generally, if you get you are starting, you start from the top level to do the synthesis and to do the map trace, to simulation and all these things. But I think generally I would just do the simulation. So here you click on the simulation file part. That means you want to generate VHDL simulation file, okay, for the simulator to work. Yeah.
You would then skip the synthesis step, just go straight to this VHDL simulation?
Yeah. Because this all the file has been debugged. Okay, so you don't all the problem basically have been solved. But if not, it will show lots of errors. And when it shows an error, you can try to fix it and then only do the compilation part of it to do the error checking. Okay, and when you solve all the logic problem, you can go to the step and doing the mapping and all these subsequent activities. But in order to do simulation, you have to get through this step, okay, and produce the simulation file. Okay, you select this one, and then in the process menu, and you do the run all.
You didn't actually select.
Beg your pardon?
You didn't select.
Yes, I selected. It's highlighted.
You don't have to
Sorry.
you don't have to check it?
You don't have to check, because the check is after it does all the process. If it succeed, it will put that check mark there.
Oh, I see.
Okay, it's not for you to check. You just highlight it. Yeah.
But I can select it. It's just
You cannot select it. Okay.
no, I can.
You can?
Yes.
Oh well, I don't know.
If you go to select it, does that mean you're saying manually, you're forcing me to say this is okay, check, this is okay?
No, don't know. Okay. Well, this is what I usually do. Okay. I just highlight this one and check the process. Okay. And it starts to do the and
I'm running
yeah.
right behind you.
And then, you know, if it succeeds in doing it, it will put that check mark in the box, I think. Okay. Oh, sorry. It put the check mark there. Okay. Yes, I think you can put the check mark there to specify that's what you want. But if you just highlight it,
You can remember.
yeah. And then I think if you look through the this process window, I think you can see, you see here, this check mark is succeeding in doing the mapping, and it is succeeding in doing the place and route.
Oh, yeah.
Okay.
Coming down, walking its way down.
Yeah. So it if it succeeded in any of because at the later, if you select the later stage, it has to finish all the earlier stage. But if you want to save time in the process window, you can say run, and that just run the one you selected. When you say run all, it just start from the very beginning and go through every step until the last step you selected. Okay. So here, I think we have the no, not here. So we have complete successfully. Okay, and that means we can do simulation. So simulation, I think it is here to check the simulation wizard. Okay, and in here there's lots of options because you have a simulation and simplify is also another option. Active HDL, lattice, these are all there, but they are there, but they are not really there. Okay, so only this simulation wizard is working with the free IDE. Okay, so the other things you select them, it would you run into dead ends because you don't have rights to these tools. All you have, all the Lattice provide you in the free version is this simulator. Yes.
So when you create these programs on the right-hand panel, it looks like you have to create the whole thing and then check to see if it works. So how do you debug something that long where you have to have it complete before you can even test it?
Oh yeah. Now when it is it's compiling or when it's synthesizing, it will give you error messages.
Right.
And you click on the error message, it will jump into the source file.
You have to write the whole thing first. You have to write
Oh
the
yeah.
entire
Oh yes.
program
Oh
first.
yes.
So
Oh yes. Oh yes.
you could be doing something philosophical wrong right at the
Yes. Yes. Yeah, we all do. We all do.
You can figure out how to break your project
Right.
down into a small little gate.
Yeah, that's what I'm trying to.
There's the difficulty.
Yes. Yes.
Is
Yes.
how do you build up from one gate to the next gate to the next gate to the next gate?
Yeah.
Yeah.
And actually, if you follow the instruction from a VHDL textbook, they don't recommend you to do it this way in one file. Okay, it actually asks you to break down everything into small chunks. You know, each each registers a couple of do all the multiplexers in one place, to do all the thing in another place. But I found out, you know, everything just fit in one file. Okay.
It came up and said that it was for the inside FPGA by Ting with only Altera. When you originally developed this on the Altera before you ported it over to this Lattice, did you do that? Did you develop each module separately, or did you do this monolithic?
I think the very early in this process, I was doing modules according to the book, but later I found that it's not that complicated. That you need, yeah. And so you see, I only have the CPU module, memory module. I have to do the memory module separately because it is your different tools, and then the UART and the GPI and GPIO. So these are.
But the VHDL was able to transport pretty smoothly from Altera to the Lattice. I mean,
Yes, all the except the memory. Okay, yeah, all the I think all the VHDL file ported very smoothly without any change. I think from Altera to Xilinx to actually from Xilinx to Altera to Lattice.
That's the goal.
So
is that VHDL is portable.
Yes, it is.
Those 5 files were
Yeah.
portable, and
Only the main file has to be resynthesized. Okay, let's do this simulation. Okay, it says it's a simulator. Okay, I have to do the EP. I really don't understand why it is asking me every time, but I don't mind doing it. Okay.
So what is it? You have to use the same name or what?
Oh, well, I think it just asks you a name to put in the simulation files. Okay. So the simulation has lots of options. I think RTL is the one I usually do. I think only RTL worked. If I select anything else, it generally failed. Okay, for no good reason.
Did you have to separately install it in the simulators, or were they?
Yes, you have to simulator. Let me see. Yes, this one you have to install if you. So you have to select the simulator wizard.
So, was there a separate installation for?
Yes, I think so.
So,
Yes, this is the only one that worked.
right, but then
Oh, I don't understand
okay,
it.
okay,
Yeah.
You may have, this may be a Linux issue.
okay, all
This
right.
may be part of the Linux install.
Yeah. Okay.
How they're gonna do the simulator.
Yeah, I think the simulator, it's using the HDL simulator, but only the version that the HDL gave to Lattice for distribution in their free IDE.
Right.
Yeah.
Most of this stuff is external tools.
Yeah. Right. This is an external tool.
Yeah.
So let's just go through, click through the thing, and not asking any special favors. I think the HDL, okay, active HDL is the one that's the FPGA Lattice edition. Okay, so this is the one that they gave to Lattice, or Lattice bought it and got permission to distribute it free with the Diamond IDE. Okay, so it is thinking, takes a minute or so. And actually, this HDL tool is doing the entire synthesis by itself again, and then produces the proper signals. Okay, so here we got nothing but straight lines. That's because we haven't specified the clocks and the reset. Okay, so what the most important thing that we need, because we have everything in this chip, the memory, the program, everything's inside one chip. So all you have to supply externally are the clock signal and the reset signal. And the reset signal is related to the reset button here. Okay, so it is connected to the reset button. We haven't done that yet. Okay, at this point, don't worry about the actual I/O. We just worry about the chip itself. Okay, we need to do the select the clock. Okay, the clock. You just right-click, and it gives you a pull-down menu, and select the simulator. Okay, so for this, the simulator would provide the clock and the reset, but you have to select what you want. Okay, so the clock it defaults into a 10 megahertz clock. That's okay. The chip, the actual clock is 50 megahertz. Okay, 50 megahertz doesn't work. All right. So, but for simulator, it doesn't mind. Okay, you can change it to 50 megahertz. It still works, and 10 megahertz is fine. So let's just apply. Okay, and close. So we will apply the clock to A clock, and then the A reset. Okay, the reset. Probably
over a little further. Yeah, you're into a Zoom mode.
Yeah.
And you'll click on the word.
Click on the word.
Nope, that's not working either.
Well, I think this is Windows 10 thing.
I'm getting that occasionally too, but holding it.
Sorry.
Eventually, I can click on it enough times to get rid of that menu.
I don't know what. Have to. I have no problem with the A clock, right? Oh, it is showing the same thing. Oh, there you go. Oh, I don't understand it. Okay, so here, the reset signal. The clock, I mean, the reset on board is a 1 normally. If you press the key, press the reset key, it goes down to 0. Okay, so the reset signal is a 0 logic and a 1, yeah, active low. So you have to set the this. So I set the 0, say 200 nanoseconds. Oh, let me see. This should be a 0. I think that was my problem, and a 1 after 200 nanoseconds. Okay.
Dr. Chen, I lost how you got to that Windows. I have the reset up, but I don't get those.
This one is to right click. Okay, you have here. Oh, sorry.
So yes. I have the reset, but how get those choices?
The choices is press this F, the function. Yeah. Okay. So press this this formula. Okay. And then you want to start at 0 second with a 0 and turn to 1 on 200 nanosecond. So I'm resetting it for 200 nanosecond and release it to be 1. Okay. So I think that's all you need to apply. Close. And this run to 1 microsecond. Okay. Now it defaults when you start up the simulator. Look at all the signals in the top module, and then try to display all these signals in the waveform. So let's don't worry about anything else. Let's just set this to the clock and reset signal properly, and I think it should work. So restart it. So from time 0, and then run. Okay, and it asks you how long do you want to run it? Well, generally I say 10 milliseconds. That's a long time. Okay, normally when you are debugging, you just run it at 1 microsecond. You would see most of the signals. But this one, I wanted to run it to see the UART. Okay, so the UART is very slow, even at 57,600 baud rate. Okay. All right. So I think it is syncing. It is simulating. 10 milliseconds is a long time. I hope it would. Okay. Wow. Yeah, it runs. And so the first thing you want to look at it is the address signal. Okay, the address. And basically, if a computer is running, the address is most likely incrementing. Okay, so it is executing instructions in sequence. So if it is anything but incrementing, the design has trouble. Okay, so here we have run to the very end of 10 minutes. So 10 minutes, I don't know, 10 megahertz, it's 1 million, maybe 1,000 or 1,000 instructions. So that's a long time. Let's just go to the very beginning. Okay, so this is at the very beginning, time 0. You see the address start from 0, that's reset, okay? And when the A reset is released to 1, it starts executing. And it has a 1 and 2 and 3, so it is actually working. But there's the time scale. It seems the time scale is too fast. So here is the minus button you can push. It just shorten the time, so you can see more clocks. Okay. One thing, when first get everything done, all the logics fine, and the simulator is okay, but run it on the board doesn't work. For a number of weeks, I was stuck there because everything the simulator says it works. Why doesn't the board doesn't work? So I was stuck there for a long time until I said, well, maybe 50 megahertz is too fast. So I reduced the clock speed to 25 megahertz. And you can see the A clock is running at 10 megahertz here. So the B clock runs at 5 megahertz. And only after I reduce the speed to 25 megahertz, it starts to show signs. what sign? You know, these things are if all the clocks seems to be incrementing, when this time when I execute a jump instruction, it jump to a new address. All these things when you call, and then you the return address is kind of saved, and all these things. When everything is working properly, you can see the all the signals. And here in the so it shows lots of signals, but most of the signals are either duplicate of other signals, or they didn't carry much information. So you may want to look at the signals inside the CPU. Okay, so here by default, it shows all the signals in the top level module. And if you care about, when you're debugging this thing, what you really care are the registers inside the CPU. And you don't see it here. Okay. How do you get the low level signals in the other modules? So here, this is a hierarchy panel, and it shows the top level design, and it has a plus sign there, shows that there are components in this module. So if you click, and you see there are 4 modules plus other signals. Okay. And what I think most interested is the CPU module. So CPU module. Okay. If you click there, this name panel shows all the signals in this component. And these, there are things, clock and clear. These are the same signals from the top level module. The address, these we have seen here. But if you go down here, you can see all the names of all the internal registers and internal signals. And you can drag these signals into the panel, and then the simulator will show you the internal signals. But before I do that, what I really want to show you is the I/O. I think if I reduce the scale of the clock, just keep on reducing it. I don't know whether I have reduced it far enough, but what I want to see is the UART. Yeah, see the UART signal. These are the UART out, UARTX. This is transmitter. Okay, so the transmitter is producing some signals. This is what I want to show you. Okay, and I like to read this signal. Okay, one more. Okay, these are the signals, the sign on message. So it is here. It's the first ASCII is an A, and that's the A is line feed. This is line feed, and this is a D, which is carriage return. And this is an E, this is an P8080. So these are all the characters, the sign up characters that you will see if you have the hyperterminal hooked up to it. Okay. Hmm? Okay. This ASCII is an A.
No, I can't get it here.
Oh, and
No, I need to.
okay. Did you set the clocks?
I set the clock.
You don't have the clock.
The clock is there.
Yes. Okay.
Simulators is
And
that.
yeah, and apply.
Apply.
Okay.
And close that. Then
Okay, and
this is
reset.
Reset is there.
Okay.
The function. 0 and 2 and 1 at 200 nanoseconds.
Yeah, that should be
right.
Should be right.
Oops.
Okay.
I
Apply.
unchecked them.
Just apply. And close.
Close.
Okay. And go to the simulation and restart.
Restart simulation.
And then run until.
Oh, it's not. See, it's still running. It thinks.
No, it has stopped because it says 1 microsecond already.
But that's all it's got there. But see, this thing, these are still counting because I told it to run again.
Oh, I see. Well,
maybe I need to start again.
Yeah. Okay, let me go to the next step. So this is the simulation part. Okay, and the simulator works. No problem. You know, when you see sign on, generally I say if the computer says okay, generally it is okay. Okay, so when you have the sign message there, because to produce these characters, almost everything has to work. Okay, but if there's any problem there in the force engine, you won't get these characters. Yes.
Simulator, or how does these stimulus generated? Is it generated by the tool or?
By the tool, the simulator, the HDL tool. It takes all the code, and then it generates the try to produce all the signals. Okay, and when you in this design. Externally, you have to put in the clock and reset signal. That's the only two external signal that's required for this thing to run, because everything is inside. The memory is inside, all the modules are inside. So, so here the simulator takes all the logic and do all the calculations and try to do output all the signals that you wanted. And in case here, I have a UART module. And this UART module, if you write into the, if you write an ASCII character into this input register, it will produce the ASCII code on this UART line. And it just put out the proper signal for the ASCII code. Okay? And now we wanted to actually run the system. Download it here to the board and try to run it. Okay, just before I do it, let me just show you that this thing actually worked. Okay, I hope. let me get on the hyperterminal. Hyperterminal. Okay, as I said, hyperterminal has been unbundled since Windows 8. But you can find this DLL and exe files in an older Windows machine. And you can pull out these files, and the hyperterminal would still work, but it doesn't work fully. It doesn't, generally hyperterminal generally would save okay, it recognizes COM4. Okay, all your COM4 is not quite right, but since I have accidentally installed the Windows 10, nothing worked the same. So I would just assume that this is still working. You have to do 57,600 baud, and the no flow control. Okay. Oh, it doesn't work, but that's okay. We'll just leave this in open. I think for a long time, this force is very unstable until I kind of move the some register out of the way. So in the last implementation, it stays on this board for about a month. I just turn things on and off, and it still works quite well. But we haven't downloaded, so let me try to download. If everything works, I should get it revived. Okay. Okay, I'm done with the simulator. Okay, back to the IDE. There's one file missing. Okay, and this is LPF. The LPF, and that's the pin specification file. That allows you to assign signals to physical pins of the chip. Okay. So this has to be set up correctly. And if you look at this file, as it is loaded, initialized normally, it doesn't have much of anything. Okay, so you need to copy all the right signal assignments. And let me open up another file. Let me use the EP, the X. All files. Oh boy. Let me see where it might be hiding. This is the Windows 10 that I don't understand. Let me do it again. Maybe I should look it up in let me see if I can find it here. I want this LPF. Yeah, LPF. LPFX. I think which one is the later one? 316, 319. This is the later one. Okay, here are all the signal assignments. Okay. I think it is in the release in the whole package. Okay, this LPF file. Yeah, it's distributed. Okay, I just when I loaded the initially add files, I didn't include that one. So the system just opened up a blank file for it. So I will copy the entire thing. I hope. I don't really need this the top line. Let me look at another file to see if it is. Yes, it is. It is distributed. Let me. Just yeah. Right. I didn't do that. I should have done it, but I thought that this is such an important thing. I think it's worth doing it. It's not all the files and the EP. Let me see this one. Okay, yeah, this one is what I want. Okay, because the other one has the copy. All right, so this one. Save. Let's close this one. And this actually specifies the pins that the signals to the physical pins on the chip. All right, I think we have this guy. But now this time we need to do the JDEC file to produce an image for the FPGA. You have to select this guy. Let me see. Let me see if I click this one and do the process, run all, rerun all, rerun all. Okay. And I hope that would, if it is.
That run is the piece that I was missing.
What?
That I hadn't figured out before. How do we get those files?
Okay.
I was always complaining the files were missing.
All right. Okay. Now it's going to do the synthesis, do the mapping and the routing, and then the timing analysis and the whole smear things. And and it's still not finished. It has lots of things to do. And I hope that this would work, but don't disturb it. It has a phase 0, phase 1, and I think the synthesis tool has lots of work to do, and in translating the logic you specified in the VHDL into actual gates and their connections on the chip. So most of the messages I don't understand. And here's some warning messages I should have been looking at, but I didn't, because it seemed to have worked. Okay. And the one problem that we had, I suspect that when I brought up the hyperterminal, it says COM port 4. COM port 4 is not quite right. Okay. Generally, I get COM 9 or 4. Whether this is a problem with Windows 7, Windows 10 when I
The update from 7 to 10 would have reset all of those settings that you saw before.
I would suspect that.
So now it's going to come up with new numbers as you plug things in.
Well,
there is a way to change that number. If you ever want to know.
Okay.
I know how to change.
Okay. Now let's see if it works. I think that could be a problem. Why this thing doesn't work now? Before I download a new copy, but we have done a new design. We successfully simulated. We have produced, I hope, the proper file, the image file for the. Let's just see. Yeah, I'm really sorry that I pushed that wrong button to get the Windows 10 up.
You can get back Windows 7. I think I saw a article.
How to uninstall. Okay, yeah, I will search for it. Okay. Let's see. Okay, I think I'm ready to do the downloading. Here, programmer. Okay. Programmer getting started. I think it sees the FTUCB. Okay, I don't know. I don't understand anything here. So I just click OK. Wow. I think it detects the through the USB cable. I think it detected the chip. Okay. Yes. But okay, it has everything. It detects the cable. It sees the port, and I think it recognized this chip device. Okay.
Got the same thing.
So I got the same thing. I think it can't choose between the two. It's yellow because it wants you to pick.
Okay.
So you do the drop down and pick. That part I got.
Please manually select the correct device. Okay. Well, I thought this is the correct one.
No, it is. But you need to do the pull down.
click on that box.
Okay.
On that yellow box. Is that yellow?
Okay. And pull down.
Yeah, and the one that you've got, the 5E is, I believe, oh, is it LFX or?
Yeah, I thought it is F.
It's not the LA, it's the LF. It's the FX. The one that was there. Yes. Okay.
So,
Okay, discussion, fine.
okay.
Okay.
And I think I need to find the file, JED. This is not the right project. Okay. So here is the EP80 in the implementation. Oh boy, I think it doesn't. No.
Should have been up in the implemented there. Should have been there. Just created.
So I don't know.
See, I'm not sure that it created the JDID.
Right.
file for you.
Yeah.
I think, well, you've got, oh, you didn't do the.
Simulation file.
Yes, click on the JDID file.
This
rather
one?
than the simulation file.
Oh, okay.
That's what's missing on yours.
Okay. This one?
Yes, click there. Yes.
All right. Okay.
Now
let's repeat that.
Rerun all. Yeah, yours didn't say done.
Right. Okay. I need to go to the bathroom. Just talk among yourselves.
Dr. Ting? For
Yes,
social
yes.
engagement at
Okay.
a wedding.
Yeah. It's so nice to have
I
you.
would rather fourth program than go to a wedding.
Okay.
But
Yes. Okay. Let's see if it is done.
Yes. now you
Okay.
have the Z file.
It's done. Yeah, it has.
What was missing before.
Yeah, I think we got it. Okay. Let's see. There. Let me close this guy. And do the programmer again. Okay. Then let me see if I can get the Y in the implementation. Yeah, I got the file there. Okay, I got it there. All right. Then you see here all these buttons. And I think the last buttons are doing anything program. All right. Successful. Okay. Yeah. Okay. So this four LED lights specified in the reset options. So I specifically light up these four LEDs. Yeah. Yeah.
We've got 4 LEDs.
We got 4 LEDs. We're
Okay.
seeing the text.
Yeah.
I've
That.
got 8080.
Uh-huh.
Version 2.3.
Uh-huh.
Then what?
Then what? It doesn't respond to keystrokes.
Doesn't respond to. Well, it's the terminal problem. let me see. Okay, here, if this is let me see my terminal.
Yes.
Yeah, I got it.
Yes.
I got. Okay, I got it. Okay, so if I do code and if I do words, there you are. Okay, all right. Yeah, COM4 is the right port. Okay. Yeah, yeah. And, okay, I think it is probably just terminal problem.
I'm working on it.
Yeah, you have the sign on message, and I think that's everything's alive on this side. Okay, and it's on your side probably. You have some.
It's not responding to keystrokes.
Okay.
It's the same problem Dennis is
You got it.
I got output, but I don't have input.
Okay. Okay. Yes, there's a reset button. Yes, this single is a reset. Yeah. Okay. All right.
It's not working yet.
Let me see. Let me push the reset here. Yeah, it resets. Okay. Yeah. So I think you have to allow Windows to do the proper thing. Anything else, no guarantee. Okay. Wow. You got the LED lit up too. Yeah, I think it's the terminal problem. If you have the okay. Yeah, I'm glad to see all the LEDs lit up. Any? You got it there?
I do.
Yes, the same thing. The same thing. The same thing. So.
57,600.
Okay. Why your LEDs not? Yeah. Okay. Okay. So that's. Mhm. Okay. 1, 2, 3, 4, 5, 6. So we got 6 success so far. Okay. I think I got the it's the terminal emulator. If it worked properly, it should be talking to the board. And the 4 LEDs, let me show you why 4 LEDs. Let me go back there and go to the EP.
And I have noted, seen some differences in the files from what you're showing us here.
Okay. I think it is the in the GPIO module, and the GPIO module has a very similar thing. You see here it on the reset. This is a process. GPIO is a very small finite state machine, and when you clear, when the reset signal is up, it would say the GPIO direction register is a 1, and which specify only 1 LED to be lit. Okay, but once the clock the clear signal is released, it sets up the direction, the least 4 bits, least significant 4 bits as a 1 that specify these 4 LEDs connect to output ports. So by default, when this LED logic is inversed, so when I'm by default, it's outputting at 0, but the LED lights up when you give it. And I think if you the port, I forgot the port number, the FF. Well, let me just don't think on my feet. I have some demo to turn this on and off, but I forgot the exact port address.
Zip up all your files that you've got there and send them to me.
All the files.
For this project.
Oh, well,
Well, I
it's a,
suspect that something's changed.
okay, yeah. Okay, this is the workshop folder. Just copy everything in the workshop. No, it's open. Oh, yeah, yeah. Yes.
Additional setting for the baud rate. Beside the baud rate, parity set to none. This page.
None. Set to none. No parity. Okay, got it.
And anything else? Any other?
Let me see. The stop bit, 1 data bit parity none, and hardware none. It seems to be okay.
When I open the ports, it's all battery behavior.
Yeah.
You just keep on running.
Yeah. Okay. Well, don't worry. Worried about when you get home. No hardware flow control. Yeah, I'm quite happy. Yeah, I'm very happy with. Well, I'm kind of happy with hyperterminal because I got used to it, and if I do anything else, I feel kind of handicapped.
And I was also hooked on hyperterminal. There's a grandfather project, Hyper Access, that is the grandfather of hyperterminal.
Okay.
It has a lot more features, and I've used that for a while. And that's paid.
Yeah.
You go to the guy that wrote hyperterminal. He's in Michigan, and I've been using that for a while. But lately, for almost everything I do serial, I use PuTTY. P-U-T-T-Y.
P-T-T-Y, okay.
Is free. It's even for a long time they had stopped maintaining it, but there's a guy that's actually maintaining it now. They've updated it for Windows 10. And that's the most popular I've seen out there. This PuTTY.
Yeah.
PuTTY works wonderful.
Okay.
It has tons of controls. It's like most of the stuff, there's way too many controls.
Okay. All right. Yeah, you can try it.
I suspect it's not.
But
Well, you're working on that.
okay. Yeah, I think that there's another port over there. Oh no, let's
So we know for certain we're talking to the right board. Okay. So where's your see that? Yeah. Maybe not on the right COM board.
Yeah, look, close it, and I think it's probably picking up another board. Close it. Yeah, let me do it. Yeah. It's the just say yes and say no. Okay. Let me get the time terminal up again. No.
You're basing it on a snapshot of the files and trying again then? So what are you doing?
Doing a config.
Yeah, COM4. I think that's all right.
Between the two.
No, doesn't work. Doesn't work. Okay. Sorry.
Okay, that's weird. I'm getting text on my end. That's really strange. Okay.
Yeah, that's a shame. That's a
All right,
shame.
no, that's something else then. No output, I'll change the symbol. I see output here right now.
Okay. Let me to the subject of PTP1 and show you a little bit about the the progress or the lack of it. Okay. Let me a new open another project. Open. Okay. I want the PDP1. The PDP, I got so many PDP1 projects. The one which is correct one, that's this one.
when you get a chance.
Okay.
Zip up what you have on your computer.
The project.
Yeah, just the whole project.
The whole project. Okay.
Well, that's what we'll get.
Yeah.
We'll get the.
Sorry. And then let me go back to that.
When you get a chance.
Okay. Yeah. Let me. Okay. So this. Well, it's still reading the COM4, the same port. Yes, I've unplugged mine.
It shouldn't have come in as COM4.
Yeah.
It should not have come in as COM4. I'll bet that terminal was not actually alive.
Okay, that could be, but
you have to find out what the port number is.
Yeah.
It's very likely what's going on.
But I'm always worried about plugging and unplugging it alive. Yes. Okay. Let me just talk a little bit about the PDP-1. Okay. And so this is the project. And if you look at it, it's very similar to what I'm doing everything from the same mode. So I get the PDP-1 and the PDP-1 chip and the let me see, memory module, and then everything else. So they are externally look very similar. The PDP has a very strange I/O structure, because I think at the time the I/O implementation has not been standardized. So they just hook up a terminal, hook up a tape drive, hook up anything, and try to make it work. So I think the tape punch, the first thing they install is the tape punch, and then the tape reader, and that terminal, a TTY or something like that. So these are all, I couldn't find a very standard way of implementing the I/O. So, but that's not I'm not seeking perfect compatibility. So, and I don't have this tape drive. I don't have the tape reader and nothing. No, do you? Well, yeah, paper tape reader. Well, yeah, well, the but the I know that the Computer History Museum got one restored. So now I took lots of exceptions in the implementation. One approach is that we just recreate the PTP-1 exactly, and so that you can still play the Star Wars game on it. Yeah. So that was a goal for the PTP-1 restoration project. And I just want something to run, something to run forth, and that is require many deviations. Okay, for one thing, it has look at the instruction set. It has an memory increment, and it has a memory increment and skip positive instruction. So these are very nice instructions, but I need decrement. It does not have decrement instruction. So I have 4 empty slots. So I put it on the decrement and then decrement skip positive. So that's for the loop. And another thing is the shifter. The shifter. It's really a barrel shifter. Okay. So 18 bits, you can shift left 8-bit or left 9 bits or right 9 bits. And then the shifter can connect with the MQ, the multiplier divide register, which is called I/O, not the MQ. It's called I/O because it tried to run I/O through that register besides doing the multiply. So the shifter is very sophisticated. You can shift up to 9 bits in one direction or in the other. And you can combine this accumulator and I/O register and shift both as a 38 circular buffer. And for a long time, I thought, well, it will take so much more logic to do the barrel shifting. I can do it, but each bit would have to have a multiplexer in front of it, which would accept the 36-bit input. So if I do the 36-bit multiplexer for all bits, for all 36 bits of the accumulator and the I/O register, I can do it. Okay, in a single cycle, maybe not. So I thought that that's too much. I just want to shift 1 bit left, 1 bit right, and to do the multiplication and the divide. So that's a deviation from the original set. And in one of the manual, strangely, it mentioned that when you do the shift, the lights, the indicators doesn't reflect faithfully the result of the shifting. That was because if you are shifting 9 bits, okay, it takes some time to shift 9 bits at a time. Okay, so I think they have some problem there. So I deviate from this 2, and then the indirection bit. If the instruction the indirect bit is set to 1, then the memory does not provide just the data; it provides an address. So you have to go fetch the content of that address. And if that address, the content of address has this indirection bit set, you go to another level. And indefinitely, okay? That's too much, okay? Yeah, it's good. Yeah, if you have the indirection mechanism set up, you can just do it whenever if the indirect bit set, you just go do another read or write. But the problem I'm facing is I wanted to run 4th program, and the 4th program I need the I have to read it's the name. You see, yeah, we have 6 bits. It's the name field of 4th words. So these are only 6 bits each. So I actually can put one ASCII character subtract 32 into here. So we ignore all the control characters, just have the ASCII part, 6-bit of ASCII part. So I can put 6 characters in a word for the name field. Okay, in the name field, the first word is count, right? That's a count. And generally, I think I would use a 5-bit for the count and 1-bit for the immediate. So that's a fourth word. But here, this indirection bit, there's no guarantee that this indirection bit is a 0. Okay. So if I'm reading this word, I'm not going to read this word. I'm going to fetch something totally bogus. So this is not if I allow indirection indefinitely, I cannot implement fourth with the proper name field. So my decision was that I would only allow one level of indirection. So only when you are executing one instruction, and if in the indirection bit in that instruction is 1, I would fetch the address and then get the data in the next cycle. But I do not allow the memory the contents of memory having that bit set as indirection bit. So with these exceptions, I was able to write my VHDL files. And basically VHDL file, the other PDP-11, the top file, UART and GPIO doesn't need to be changed much. And only the CPU part needs to implement the new instructions. But the new instructions are not, you see, there are not too many instructions. It has a 5-bit code field, so it allows 32 instructions. But among certain instructions, the skip, the rotate, skip, and IO, these instructions use the address field for other purposes. Okay, so even there are only one instruction, they involve many different variations. They can skip on positive, skip on 0, skip on non-zero, skip. You can skip over lots of different things, but it's only all one instruction, and you can rotate or shift all different things. It's only one instruction, but with bits specify whether it's left shift, right shift, shifting the accumulator, shifting the IO register, or shift them combined. And then the last 9 bits, you are shifting that many bits, but it does not give a shift count. It's counting the bit ones, the 9-bit field. If there are how many ones, it will shift that many bits. So if you just shift 1 bit, you have 9 different ways specify shifting 1 bit. Of course, if you want to shift 9 bits, then everything's 1. And this is too hard to write in VHDL. But I think I can get by with only a single bit shift. So here, let me show you what I want to show you is the simulator, okay? So I do the simulation file. Yes, this is PDP. Let's just rerun all. What else? Oh, the other thing is the E4. So for PDP1, I have to write another fourth. For the 8080, I have Z80 implementation, Z80 fourth implementation. So I took that implementation. The Ken Chen in Taiwan, he wrote, he ported the E4 to Z80. So I have that. He used Mason. He used that. I was hoping that he's not using any of the Z80 code, and he only used the 8080 code. Then doesn't I can port it. But unfortunately, he used several Z80 code, and the Z80 code, I think it's 1 byte less than the 8080 code. So, but I was able to jerk around and get the Mason to assemble everything and get the project up. But for the PDP-11, I thought I could use Mason to do it, but that's hard because this is an 18-bit processor, and Mason is basically byte-oriented. Or for the 8086 implementation, I actually have 32-bit words. Okay. It was very hard to change the Mason to compress the ASCII code into 6 bits and fill this in. So all these things, I thought of rewriting the macros to accomplish that, but I don't have the thought process complete, and I don't know Mason that well, or I forgot most of the Mason tricks. And but I have the Chuck Morse assembler for MUP, and I've used it for EP16 and use it for EP32. So I use that MUP assembler, because you see the MUP, the problem was fitting 5-bit code into 16-bit or 20-bit word. So I have all the mechanism in that assembler. I have all the mechanism to fit things nicely. So that was I used that and wrote the PDP-11, PDP-1 assembler, and then write the kernels and the E4 system all in fourth. So let me show you this assembler, and show you how this assembler how it worked. So this is a very, I think, very important part of CPU development. Because you have to have, you either write a test bench, which I think is much more difficult than a CPU itself, or write a fourth, which becomes the test bench. And then you have a free debugger with it. here is the way I'm trying to do the assembler, and this is using the an early version of F# called WE4. I think it is WE4 201 or 22. Where is it? Yeah, WE4 okay. So here, this is the meta. This is a meta compiler. So basically, it opens a fourth virtual machine in that it puts fourth instruction into this big array called RAM. 8,000 hex byte for it. I don't need that much, but that's what it is. So you have logic addresses, which address 16 bits of word, and 16-bit words are put in to a 4-byte word in here. And you have an word address you have translated into the real address and do the fetch and store into this array. And this way, when the assemble runs, it assembles bit patterns into this array. And you can show the contents of this array just fetching each 32-bit word. You only use the 16 lowest bit for storage, and so it's quite convenient. And then the assembler. No. When I double click it, the whole thing just run. Open with Notepad. And this is the assembler. So the assembler knows basically, you see the comma in fourth. Comma just add one word to the top of dictionary. And this comma was changed to W comma, so that it would write 18 bits of word into the virtual memory for the fourth virtual machine. So you can I just input the code portion of it, Y put the address portion of it into an instruction, and the B is try to take ASCII 8-bit ASCII code, try to compress it into 6-bit, and then stuff them into the various slots in a word. And so here, the command B, it just stuff this 8-bit characters into a word. Yes. It's in the F# style.
Oh, F#.
Yeah, or the V4. This is a WE4. Yeah. And so here, this is the assembler, and this is the how to build the header. The header, you have to put in the count first, and then fit in the ASCII bytes. If one word is not enough, you open another word, and then you can stuff up to 3 bytes into the name field. So these are all to build a searchable dictionary. that has the proper name fields for link field and the name field for searching. So this is the assembler. And here are all the instructions, the PDP-1 instruction. So PDP-1, everything is in octal. All the different instructions that's being implemented basically up there. And then the skip and the shift instruction uses the address portion to specify specific skip conditions and also the shift conditions. So all these things can be, all the assembler can handle all these different PDP-1 instructions. And then the kernel, which I am very proud of. Okay, the kernel first, these are the user variables. And they are all defined as a constant because I kind of use all these variables are fixed at the fixed locations. I'm not trying to do multitasking. So only one copy of the user variables is sufficient. And then here is the inner interpreter. The inner interpreter, the most important things is do step or called next. So this will, you have a list of addresses. You just go through them one address at a time. So this, the pointer is the IP. So all the high level words are a list of addresses. You just go through, use IP to point to the next word that you want to execute and then jump indirectly into it. So this is the next. And at the end of every primitive word, you just jump to that. So it is a macro, you jump to the do step. And then for every high level word, you start with a do list. And you do a call do list. And the PDP-1 doesn't have a very good subroutine mechanism. It doesn't know stack. Okay, so what it calls subroutine call or jump to subroutine is a call and it saves the program counter, which points to the next instruction, into accumulator. And then you have to deal with that address yourself. Okay, so it's one level subroutine call. And so here, what you do here is to do the, you have the address in the accumulator. So you first deposit that accumulator into the AC variable, and then decrement RP, and load IP into the AC, and then deposit the AC, the content of IP into the return stack. Okay, and so you save the IP on the return stack, and then you you load the actually I think load the AC which contains the which has the pointer to the next word to be executed, and you put that into IP and then jump indirect to it. So this is in front of every high level word, it has a jump to subroutine do list. and then it processes the following list properly. So that so these are the do count is just return the address. You see the accumulator is pointing, which is the constant you store there. You just fetch it out, and you got it. Or when you do the variable, this address is what you need. So you just get the address, push it down to the stack, and you're done. Okay. So these are the inner interpreters of it, and then the kernel. And then kernel, the branch, query branch, do lit, exit, leave, do next, execute, and then all the rest of it. Okay, and then the high level code. So all this in the kernel, all the user variables are used as constants because they are constant addresses. Here in the kernel, in the high level, you have to define the user variables so that they can be compiled and then they return the constant address when they are executed. So here are all the user variables. This is still the kernel. Where is EF? EF's here. Okay, there. And then all the high-level words that constitute the interpreter, the compiler, the debugger, and everything. So all these things are there, and when what do you do with it? You just push this button, and it compiles the entire kernel. First loads up the meta compiler, then loads the assembler and the kernel and the high level. So when it compiles, it spit out the address of all the words that's get compiled. This is a very nice symbol table that when I'm debugging, I need to know the addresses of each word, and these are the things that I need. And so these are all you see, after the whole thing's compiled, I got to the address 94B. This is 12-bit. The memory is 12-bit. So the last address is FFF in hex, right? So I'm a little bit more than half of the, I'm using about 2.5K words. So I think if it all worked, there's still lots of room to compile new words. And then I'll show you the thing that gets compiled. 0 show 0 show. Okay, this shows the compiled code that will be downloaded into the memory. So the first word 30891 is jump to 891. Okay, this is a jump instruction, and then the next few words from the 12, and these are the user variables. Okay, and then from 18, that's a do list, so forth. So all these things will be later synthesized synthesized and to generate the RAM memory file. Okay. In here, to produce the file that's readable by the Diamond IDE, and that's this file. So it generates a file in hex. You can see this. The first word is 30891, and that's one. And this is the format the Lattice IDE required to initialize the memory to be synthesized into your design. Okay, so that's the fourth. So I was my thinking is that I got the fourth to I got a code there, and if I load it into the FPGA, I should be able to see these instructions executed. Okay, so let's do the synthesis. I think we did synthesis, do the simulation. Ah, that's nice. It has because the clock and the reset has already been specified correctly. So I have the clock and I have the reset. For some reason, I think I didn't do the reset quite correctly. I know now I know. So I'm just using a very slow clock for the reset. Just get it to work. So this one runs only for 1 millisecond, 1 microsecond. If I run it for 50 microseconds. Okay, then I see the clocks, many more things. So if I go just compress it a little bit, some more, and then go back to see the starting. Okay, so I'm seeing the instructions being executed. So you see the 891, the first jump to 891, and for sure I jumped to 901. So this address is showing the 91, and the 891, that's the code. That's a high level word. So it does a call to the 18, and then sure it jumps to 18. And then I didn't have all the registers showing, but if you look at the register, the address following the call is deposited into the accumulator. But I think I only debugged the 4 instructions. So although it is running that seems to running quite smoothly. So 18, then to the 15, and 1A, and then it's not. I think I only verified 4 instructions, and then it goes haywire. Okay. So I'm still trying to figure out exactly what was going on there. I think it goes to 968 or something. Well, I can't read it very well. But anyway, I think the first 4 instructions were executed correctly, and then I don't know what's going on afterwards. So I'm in the process of debugging it, and actually debugging it. There's when you have lots of problems, debugging it here at the highest level is a real challenge. Okay, I think now I remember when I do the 8080 implementation, what I did was not doing it this way, but to debug the CPU alone. Okay, use CPU as the top module, and then exercise the CPU by itself. So in exercise the CPU by itself, what I was able to impose on the CPU is the memory input bus. Because if you don't only exercise CPU, you don't have memory. Okay, but you can simulate memory by imposing the instructions on the data bus, data input. So you just keep the same data while the clock is running. So this it forces the CPU to execute the same instruction repeatedly. And then you watch the registers to see if they are doing the right thing. I think this is the easiest way to debug the CPU instruction by instruction. And once, of course, you can do more sophisticated simulation, like the writing the test bench, but you are imposing the data bus with a very specific timing, synchronized with a clock, and then you can almost executing an arbitrary instruction sequence that way. But I think one thing I found in this simulator, which is not as sophisticated as the test bench allows you, is that there's only very limited patterns that you can sequence through the simulator. So the data you cannot have. I think it allows you to change 3 times. So that maybe it's enough, but I don't know. I still have to work on this one to verify all the instruction is working by imposing instructions on the CPU module, and that way you can debug most of the instruction quite accurately, but not fully, because many instructions you need the dynamics to show that things have to be working properly. So that's as far as I get, but I hope that it's helped you. It helpful if you are actually trying your own design. So just first get the simulator to cooperate. That basically checks all the logic, but it doesn't guarantee you the dynamics of the CPU. That you have to impose the clock and see the consequences. Okay, I think that's all I have to show you. Questions?
I've got something actually working.
Okay, all right.
I've got
That.
Ah,
What do you do to list the words?
words, capital.
Capital words.
Yeah.
That's
Yes, you got it.
I've got it.
You've got it. Yeah.
I switched computers.
Okay. Okay. Ooh. Okay.
No, I did everything here, fresh,
From the file he sent out.
from the file he sent out.
Okay.
So
All right.
the file, your side's right.
Okay.
Setting it up, I had set it up before and not done everything properly. That probably corrupted things. Now the question is that I need to compare what I've got here with what I got here and find out why they're different.
Okay. For the people out there, yeah, we got the success. Dennis got everything working. Okay. Yeah. Okay. Oh, sure, sure. Yeah, I think I don't change it, but it does matter, I think.
Okay, so I got that correct.
Yeah, I think it's you didn't change it. Yeah.
Oh, I'm off.
Wait.
You're at 9493.
I don't think this thing matters.
This
Okay.
one.
Yeah.
This one does, right?
I don't know. Just don't change anything. Okay. Any comments? Any? Okay. Well, let's just close. All right. That's all we have. Okay. Thank you very much. See you next time. Bye-bye.
Okay, thank you. Very good.
Okay. At least we got something working.
Yeah.
Yes.
We're done then. I can start.